And what we're going to look at today is real-life problems that can be solved with what we've been learning about cubic equations and polynomials. Certain airlines have a restriction on your carry-on bags. Have you ever seen, sometimes they have like a thing your bag has to fit in if you've ever gone on a flight. They'll give those dimensions online. And they have to have some leeway because they can't force everybody to have exactly the same size of bag. So they have to come up with some sort of restriction guidelines. And the one that they have here is whatever you bring, the length, the width, and the height or the depth can't exceed 100. Well, that gives you some range, right? You can make something longer and something smaller and still pass all of those restrictions to bring it on the plane. So they have this 100 centimeters. Now, if you're a luggage company and you're looking at this, what will people want to buy? They'll want to buy the luggage that fits the restriction that has the largest volume possible so you can fit the most stuff in. So depending on what you do, it creates a different volume. So what we do in a situation like this, I'm gonna draw a piece of luggage here. Here we go, three-dimensional.
Pardon the interruption. Can we please have all grade 10 French immersion students to the cafeteria? That's all grade 10 French immersion students. Please go to the cafeteria.
So this sentence here says several models of carry-on luggage have a length 10 centimeters greater than their depth. So what we're going to want to do on here is we're going to introduce a variable. I'm going to use x for the depth, and then the length is 10 centimeters more. This would be x plus 10. That's the only information that they've given us, besides the fact that all of them add up to 100. So what we could do in a situation like this is we could just go through some possibilities. And by possibilities, I mean, here we go, depth, length, and then I guess the other one is the width. I could make a depth of 10 centimeters, right? How long would the length be? 20. What's the width? 70. So as soon as I put numbers, you were able to find that third side, no problem. And if I draw a blue line here and put volume, we would do 10 times 20 times 70, which would be 14,000 centimeters cubed. And I could put 20 in. If this is 20, that would make this 30, making this 50. Again, once I put those two numbers in, since they add up to 100, we can figure out the width and this one is way better. Look how much more space. We have 14,000 centimeters cubed versus 30,000 centimeters cubed. Visualizing. Has anyone ever bought a piece of luggage where they have advertised the volume? Have you ever seen a piece of luggage where they've advertised? Like, if any of you decide that you want to travel after high school, sometimes you can buy travel backpacks and they will tell you the size. And they'll tell you the size in liters. It's kind of weird. Like, you're going to fill your backpack with water, and like, I have an 80-liter backpack. You know how heavy that would be if I filled it full of water? So, something to, I don't know if you've learned this in science, but 1 centimeter cubed is equal to 1 mil of water. So 1,000 centimeters cubed is equal to 1 liter. So this 30,000 centimeter cubed suitcase, that would be equivalent to 30 liters. If we were trying to imagine that, I always think in ice cream, because I buy ice cream by 4-liter pails. So that'd be like 7.5 ice cream pails that I could put in my suitcase and melt in the plane if I wanted to. That's pretty big. But the question is, what makes it the biggest? If we want to make it the biggest, we're going to need to put down on this other side. You could do it with numbers, okay? You could do what I did 10 and 20. You had no problem coming up with 70. I'm gonna just quickly test another one. Could you, if I did 30, this would be 10 more, 40. What would the other one be? 30. You had no problem figuring this out. Now we'll go to algebra. One is x. One is x plus 10. What's the other side? You could do it with numbers.
100 minus 2x plus 10.
We can write this green side. Because 100 is the total, right? And what did we do for each of these? We had to do 100 minus 30 to get the 70. 100 minus 50 to get the 50. 100 minus 70 to get the 30. So we have to 100 minus, and these two added together are 2x plus 10. And I put it in brackets because we have to subtract all of that. Can you see that that would simplify to be 90 minus 2x? You can double check. If you take 90 minus 2x and add x plus 10 and add x, do you get 100? You do. Okay. So now we've set it up with algebra. And how did I figure out the volume every single time? I did length times width times height. And so when I go to set up my volume here, my length times width times height in no particular order gives us x times x plus 10 times 90 minus 2x, which we're going to graph. And the reason this is easy for us to graph is because it's already factored for us. We can see the x-intercepts, we can find the y-intercepts, we can look at the end behavior. So what we did in yesterday's class is we learned the shortcut for graphing polynomials was to use the end behavior. So in this one, my end behavior first of all, I have to put this and multiply it out. Do you see that if you took an x times another x times a minus 2x and you wrote this out and multiplied it out, you would have a minus 2x cubed, and your leading coefficient is negative and your highest degree is odd. So we know that our end behavior acts like a line with a negative slope. There's my end behavior. Next, we would find our y-intercept by plugging in 0 for x. I hope you can see, since it's already factored, we're going to get our x-intercepts really easily. Our y-intercept, though, if I plug in 0, I'd have 0 times 10 times 90, which is 0, 0. And my x-intercepts are 0, 0 and minus 10, 0 and 45, 0. So with our end behavior and our intercepts, we can draw this graph. I'm going to just mark 45 there, which would make negative 10 about there. Those are my 3 x-intercepts. One of them is also a y-intercept. And my end behavior, I know that I need to end down here and start up here. We also learned about multiplicity. Do you see that all 3 of these have a multiplicity of 1? And if the multiplicity is 1, your graph goes straight through. So when I go to graph this, through this one, smooth curve through all of them, it creates this graph. Now, this is the graph for all of x, because a polynomial is usually defined for all the domain. But when you're working with a word problem, there are only some things that make sense. For example, if this is my x and this is my y stood for volume, and my x, what was x originally? It's the depth or the height of your suitcase. Has anyone ever seen a suitcase with a negative height? No. Has anyone seen a suitcase with a negative volume? You put stuff in there, it just disappears. No. So in this situation, we have to also decide what's the only part that makes sense. So when we get, first of all, we do math with just numbers and stuff and get really good at it. And it's out of context. When it's out of context, the math is actually easier because you can do a whole bunch of stuff. When it gets in context, now we have to think about what makes sense and what doesn't make sense. And in this situation, this part that I've highlighted here in yellow is the only thing that makes sense. In fact, 45 doesn't make sense, because what would happen if I did 45? This would be 10 more, 55. What's the other one? That would be 0. That would be like making a tiny, tiny thin piece of paper suitcase that you could not put anything in. Not very practical. So the only thing that makes sense is this yellow part, and what we're looking for is that point. And in grade 12 pre-calculus, this part of the unit, you're going to need technology. You're going to need to either have Desmos on your phone or at home on a computer. It has a really nice app, or use a graphing calculator. And what we're going to do is we're going to take this equation and type it into our graphing calculator in factored form. So it was x times x plus 10 multiplied by bracket 90 minus 2x. And when you hit graph initially on a graphing calculator, it's probably not going to be very nice. In fact, you probably won't see very much at all. Oh, isn't that nice? Does that look at all like the graph we drew? No. And the reason is, if you can see my mouse here, your graphing calculator is set to see from negative 10 to 10, so it's like only seeing a tiny little window here. We need to see, well, it looks like the important parts are from 0 to 45. So one thing you can do on a graphing calculator is you can hit the window button, and I'm going to change my x min to go from negative 1. I want to go up to 45, so I'll go a little further, up to 50, and then I'll hit graph. Okay, I can see it coming back down, but it looks like it's going a lot higher. We did our table of values. I mean, we only did, oh, we didn't even do that last one. Here, I'll add that last one in, 30 times 30 times 40 times 30. That's the best one so far. Our graph currently is going up to 10 centimeters cubed. We know from simple mental math, so far the biggest one we found is 36,000. So my window needs to be much, much higher. And in fact, doing a couple of examples to see where things are at is going to be helpful, because now in my window, my Y max was 10,000. I have 36,000 already. So I'm going to go up to 40,000 and see if that shows up on my graph a little bit better. And now I can see a little bit better. This is what I highlighted in yellow. I'm interested in this maximum. And your calculator, if you go second, above the trace button, calculate, lets you calculate all sorts of things from the graph. What we're interested this time is the maximum. It says, is your cursor to the left side of the maximum, then push enter. Then you can arrow over until your cursor is to the right side and push enter. If the maximum is in between those two arrows and you push enter again, it will find the maximum, and the x was supposed to be 28.581, and you would get 36,209.923. Okay, am I going to remember those numbers? Not completely. 36,209.923. It's like 9 ice cream pails. 9 ice cream pails, 36-liter carry-on luggage. And that's the maximum. So if you were a suitcase making company, this is very valuable. Because if you can figure out, based on the restrictions from the airline, what makes the carry-on bag the biggest possible, more people are going to buy that. Because it's going to be the most useful for them. And so these are the kind of applications that we're going to do. Now we're going to get to your jewelry boxes right now. Draw my piece of paper. Here was your beautiful jewelry box, open-ended, in the end, 3-dimensional picture. What did you do? You cut out squares out of the corner of size X. That became your height when it was folded up. You then folded along these blue lines. And then you measured those. I noticed in some of your calculations that obviously we probably made some measurement errors because there was a couple of volumes that came up that were mathematically not possible. That is okay. So, what do we have is we would the original piece of paper, if you were working in centimeters, is 21.6 centimeters by 27.9 centimeters. That's what a piece of paper is in centimeters. In inches, it would be 8.5 inches by 11 inches. Because we still use American-sized paper. Next, what does that mean for all of our lengths? Does it make sense that this shorter length would be 21.6 minus an x on this side and an x on that side? 21.6 minus 2x. And the long side will be 27.9 minus 2x. And the volume of your beautiful jewelry box. And again, in a real life problem like the jewelry box, all of a sudden our numbers are not, they're decimals, they're not nice. Because the world doesn't, like, you go out, the world doesn't be like, oh, numbers will be nice for you all the time. But now when we go to graph this, what's our end behavior? Well, if you multiply this out, you'd have an x and a minus 2x and a minus 2x. That will give you a positive 4x cubed, which makes your end behavior act like a line with a positive slope. There's our end behavior. X equals 0. X equals 21.6 divided by 2, 11.3. And x equals, divided by 2, 13.85.
Should it be 10.8 instead of 11.30?
Yes, thank you. 10.8 and 13.85. So when we draw this one, x-intercept at 0, at 10.8, and at 13.85. And we know our end behavior has to start down here and end up here. All of those x-intercepts have a multiplicity of 1. Your graph is going to go straight through, straight through, straight through. And what makes sense in this one? Why can't I use anything bigger than 10.8? Like if I used 11, this side would be 11, this side would be 21.6 minus 22. You'd cut off all the paper and you'd have nothing left to fold up. So that's kind of interesting. You have to make sure you still have something that's possible. Here is our maximum. So now if I go to my calculator, oh, by the way, what you could do in here is say, okay, I think the maximum is going to be somewhere around 5. So we have length, width, height. If I pick my height as 5, and I think somebody had, did someone have 5 on our board? Then this side will be 21.6 minus 10, which will be 11.6. And 27.9 minus 10 will be 17.9. And if I do 11.6 times 17.9 times 5, I get 1,038.2 centimeters cubed. It's important to do one because now I know a little bit of how I want to make my window look. I'm going to go back to my graphing calculator. Go back to y equals, clear this one out. X 21.6 minus 2x. And the other side was 27.9 minus 2x. And when I go to my window, now I don't need to go up to 50. I know that the highest was around 11, so I'm going to go up to 12. And my minimum, I plugged in 5 and I got 1,038, so I'm going to go up to 1,500 just to see if I can get that maximum. Oh, it actually looks like it, like 5 in the middle, it looks like it's a little bit to the left. So we can go second, calculate, number 4, the maximum. Start on the left side of the maximum. And you can use the, if you have a graphing calculator, you could use the arrow key to get to the left side, just like I did at 2.7. You can also just type a number in. So in the right bound, I'm going to type in 6 and push enter, because it's a lot quicker than hitting the arrow key a ton of times. Then push enter again, and it was actually 4.026 and 1,082.5942. So if your volume was higher than the 1,082, you just made a measurement error, because that is the maximum jewelry box size that's possible. So again, it's kind of interesting. We all started with the same amount of paper. And initially, when I was thinking about this, I was like, ooh, I don't want to, the bigger the square I cut out, the more paper I'm wasting, right? And the more paper you're wasting, you think, that should make my volume smaller because I'm getting rid of more paper. Shouldn't I use as much paper as possible? But actually, a size of 4.025 is the best. So the question that we just did with the paper right here, I'm gonna go back to ours. The question we did with the paper is very, very similar to the question that is number 1. So I'm going to leave number 1 here for you for homework because the answer is off to the side. And I'm also going to get you to circle questions 3, 4, 5, 6, 9, and 10.